Okay, now let's take a look at Ronnie the Rational. This is example 3 from your reading. In this case, f of x is equal to x squared minus 1 over x cubed. Oftentimes you'll find one of the toughest parts for finding whether the function increases or decreases is actually finding the derivative. In this case, we're going to use the quotient rule. We could divide this out initially and we'll get to the same answer, but I'm going to show you using the quotient rule since that seems to be a favorite. In this case, f prime is equal to x cubed times 2x minus x squared minus 1 times 3x squared, which is low d high minus high d low, over low squared, which is x cubed squared. You need to simplify these, because the more that you simplify and simplify correctly, then the easier the critical points are going to be defined. In this case, when we multiply this out, we get 2x to the 4th minus 3x to the 4th minus 3x squared. It is critical that we understand that we need to distribute our negatives. I know that that's an issue, and we need to make sure that we do well with this. So, when we distribute our negative, we're going to get a 3x squared positive minus an x to the 4th over x to the 6th. I'm going to leave the answer like this for now to prove a point. Next step, as always, is to find the critical points. As always, when you find your critical points, we're setting our derivative equal to 0, or we're finding where our derivative does not exist. This second part is going to be useful now. To find where the derivative is equal to 0, since we have a rational derivative, essentially what that means is we're going to set our numerator equal to 0. In this case, our numerator is 3x squared minus x to the 4th. When we set that numerator equal to 0, we can factor out an x squared, and we get an x squared times a 3 minus x squared is equal to 0. This leaves us with 3 critical points from where the derivative is possibly equal to 0. I'm going to explain what I mean by possibly in just a minute. Those points would be x is equal to 0 and x is equal to plus or minus root 3. In this case, to find where the derivative does not exist, we need to set our denominator equal to 0. In this case, that's x to the 6th. When we set x to the 6th equal to 0, we get that root of x is equal to 0 again. In reality, x is equal to 0 showed up both where the derivative is equal to 0 and where it did not exist. Just like with our implicit functions, we really need to investigate what actually is going on there. We won't go into depth on that just yet, but we will in a future lesson. But for now, know that x is equal to 0 is certainly a critical point. Our third thing, we need to perform a sign test. So I wrote out the factored form of this derivative up top here. And we've got our 3 critical points, negative root 3, 0, and root 3. We're going to test a number in all 4 slots there. So for example, when x is equal to negative 3, when we plug in negative 3, we're going to get a positive here and a negative here because 3 minus negative 3 squared is a negative number. And a positive, of course, on the bottom because that's x to the 6th. We're going to test a number to the right of negative root 3 and to the left of 0. We get x is equal to negative 1. We're going to get positives everywhere. A number bigger than 0 but less than root 3 would be something like x is equal to 1. When we plug in, we get positives everywhere. And similarly, when we plug in something like x is equal to 3, we get positives everywhere except at this 3 minus x squared part, which will give us a negative. So altogether, we're going to have a negative, positive, positive, negative. This should make sense. If you notice, the roots of negative root 3 and positive root 3 occurred only once. But the root of x is equal to 0. When you go through and you cancel out, it's going to give us an even multiplicity on the bottom. Therefore, we repeat signs on either side of x is equal to 0. Our conclusions. F increases on the interval negative root 3 to 0 and 0 to root 3 because f prime is bigger than 0. And f decreases on the interval negative infinity to negative root 3 and root 3 to infinity because f prime is less than 0. Those 2 spots there. A pretty complicated problem, but you need to make sure that you work on simplifying and using the quotient rule correctly. I would suggest making sure that you plug in your critical values into some sort of a factored form of the derivative. It makes it go a lot faster.